So our final session here is on international lunar missions, and what an exciting one it is. And our kickoff speaker is my friend and director of the Exploration Science Strategy and Integration Office within the NASA Science Mission Directorate at headquarters, Dr. Joel Kearns, who's going to be giving us an update on two of the programs that he manages, LDEP and CLPS. So Joel, please go ahead.
Thank you, Greg. Let me project my charts. So I'm Joel Kearns. I'm a Deputy Associate Administrator in NASA's Science Mission Directorate for Exploration, which includes our robotic and human activities for exploration of the moon for science, and also to make sure that technology and engineering development demonstrations are done on the moon as preparation for Artemis. And the Lunar Discovery and Exploration Program has several different elements. We fund investigations related to the moon. We develop instrument suites in the US that'll be operated at or near the moon. Probably the thing that is most unusual for the past few years is that we get those instruments to the moon using US commercial companies under an effort called Commercial Lunar Payload Services, or CLPS. We also develop mobility systems to enable investigations or conduct investigations. An example is the Viper rover currently under development. And we also work with partners around the world to do joint studies on or at the moon, which could be, for example, using particular instruments that have been developed by other organizations, or particular technologies, such as different ways to do rovers during this early time when several nations are just starting to plan to send rovers to the moon. We also, in that program, define and integrate all the science on the US side for Artemis, both within Science Mission Directorate, which is more than planetary science. It's also heliophysics, astrophysics, biological and physical sciences, and other areas, but also other NASA mission directorates such as space technology, exploration systems development, space operations, and again, even other US agencies as well as international partners. Now, recently, the Decadal survey on planetary science and astrobiology was issued by the American National Academy of Sciences and Engineering, and it gives very specific recommendations for what work in the future should be performed by Lunar Discovery and Exploration Program, and Artemis in particular. And I'm going to talk a little bit about that as part of this update also. So you're probably very familiar with commercial lunar payload services. There are currently 7 deliveries of investigations to the moon that have been funded by NASA using a group of 14 US companies. There are actually 4 companies that have competed successfully to be given subcontracts by NASA to deliver NASA's experiments and equipment to the moon that are shown here on the bottom. And in addition to simply delivering things to the moon, NASA contracts for the operations of the instruments to meet the science or technology objectives, and also will ask for very specific services. For example, if we ask to land a suite of instruments on the far side of the moon, we need to get our data back for the instruments during their operations. So the CLPS provider has to provision some way to get our data back. What's interesting about CLPS is that NASA does not develop these landers. We don't own these landers. We don't even buy the launch vehicle to get the lander to the moon. We actually go out and just purchase a service from a US company to deliver our instruments to the moon, have them operated the way that we define they have to be operated, and then get our data back to meet our objectives. So today there are 10 CLPS deliveries in various stages of preparation. As I mentioned, there are 7 that have already been defined with their instrument suites to go to the surface of the moon. You can see those 7 listed here with icons of the landers that will take them to the moon. Of those 7, there are 4 companies doing those deliveries that they have competed out of this group of 14 to have NASA select them. And so far, 1 company has been selected for 3 landings. 1 company has been selected for 2 landings, and 2 companies have each been selected for 1 landing. We have a competition we're running today, this month, next month, and months coming up in the summer to pick the company that will take a suite of instruments to the Schrodinger Basin on the far side in 2025. We are very close to picking the instrument suites and investigations that will go to grid highs and domes, and also South Pole location. And once those are selected and made public, we will then start the process of picking the CLPS delivery company that will actually take those investigations to the moon. We pick our investigations and our research suites through a process called PRISM, or Payloads and Research Investigations on the Surface of the Moon. We have US investigators who can propose investigations with international components once a year, compete to have their investigations selected to show how their proposed research meets major questions that NASA has been advised to research by the planetary science and other science discipline communities. And then after we make those selections, which are shown here on this chart, we then go get the CLPS companies to take those investigations to the moon and operate them for the investigators. I wanted to say a few things about how we're looking at the Planetary Science and Astrobiology Decadal Survey, which was just released in the month of April. We're currently analyzing that with NASA's Planetary Science Division. I wanted to highlight 2 things that are mentioned in the Decadal Survey. One is a way to address chronology questions looking at South Pole Aitken Basin. The Decadal Survey recommended a long-life robotic rover to gather samples at many different sites, then have those samples taken to the South Pole of the moon so that an Artemis crew team could examine the samples and then bring them back to Earth. And we're researching right now how can that be done, and depending on how we do this, how that might change other elements of the lunar discovery and exploration program so that we can carry this out. But this is a very exciting recommendation, and it's got many possibilities for how it could be implemented. Another aspect which has been brought up in the past recommendations, just as SPA Aitken Basin sample return has been advised to NASA, has been to establish a lunar geophysical network. The Decadal Survey identified this as one of potentially 8 themes that NASA could select for its next New Frontiers competition. It's listed here as one of the 8, and you can see the science objectives for the Lunar Geophysical Network listed. How we do this in the future, since it's been reaffirmed as a priority, is something that we'll consider within NASA, but it was really good to see this again recommended as a high priority as a potential New Frontiers mission in the future. So we're looking today very closely at the lunar science themes outlined in the Planetary Science and Astrobiology Decadal, and how those map to the 12 big questions that were recommended as focus of study for the Decadal. And we know our advisory committee, like the League and the Planetary Advisory Committee, are also looking at this very closely. As you can imagine, now that the Planetary Science and Astrobiology Decadal Survey has been issued, this is the time for us to look at this and reflect on how we have been implementing lunar discovery and exploration program and see if we need to make any adjustments. Well, I do want to point out that there is currently quite a few partnerships with European organizations in work as part of lunar discovery and exploration and CLPS. We routinely have opportunities for international partners to contribute scientific instruments or payloads to Artemis and CLPS on a no exchange of funds basis. On CLPS, in the PRISM solicitations for U.S. instruments, up to 1/3 the cost of the overall instrument suite could be an international contribution. And space agencies can also directly request NASA resource allocations on a NASA-led CLPS deliveries, and then it's up to NASA and that organization to determine if a true partnership is a benefit to both sides. Something I'll point out, which is not on a no exchange of fund basis, is that any European organization, just like any US organization, can directly go to one of the CLPS companies and pay them to take their equipment to the surface of the moon. And there are several European organizations that are doing that on several of the early CLPS deliveries planned for the end of this year and early 2023. For Artemis, we're just now defining the process for soliciting Artemis instruments, and these will definitely include opportunities and processes for international contributions. And also for Artemis, similar to CLPS, international personnel could be part of a US payload science team, and international scientists could apply to competitive calls for participating scientists to contribute to science teams. And I've listed here in the bottom 3 investigations and instruments that are in various stages of implementing or discussion, for example, with ESA for CLPS. The MPAC instrument is manifested on a CLPS delivery that'll go in 2024. We've recently concluded an agreement with ESA for the Prospect instrument, and we're currently discussing the details with ESA, and we're currently working on an agreement to deploy the Lunar Pathfinder communication relay technology with ESA out to cislunar space. There's a very detailed planning manifest for how we're working now to start scheduling the various calls and the planning for the instruments and the science teams for Artemis. This is the planning manifest that the Biden administration released with the president's budget for 2023. This is the plan that we work to today. And this shows all the different contributions of the US from the Exploration System Development Mission Directorate to science to space technology. And there's a large number of things here for Moon to Mars planning with Artemis as well as LDEP and CLPS. And we can highlight here some of the ones that are going through detailed planning now that's taking place. As you can imagine, there's a big focus on planning investigations and activities for the Artemis 3, the first crewed landing, getting those instruments together, getting the instruments planned for the CLPS missions that will take place in 2025 and 2026, and even the crewed lunar terrain vehicle. So I'm going to close here with just showing you the upcoming US solicitations. Again, there are opportunities for international partners to participate with the US science teams. And these are communicated in the US, and I'd recommend that you watch for these opportunities as they're announced. Thank you, Greg.
Great. Thank you so much, Joel, for this great update. What an incredibly exciting time this is for all of us. That's for sure. And maybe I'll start off with a brief question to you. One of the things I've certainly seen in my own NASA career is the difficulty of integration between directorates. And from my own point of view, it seems like that's working as well as it's ever has in my career, my 37 years at NASA. But I wonder if you could comment on some of the things that you're working with the Human Exploration Group, and perhaps some of the challenges that you might have had.
I'm very fortunate in that we have very open discussions and transparent discussions with our partners in exploration systems development, in space operations, and in space technology. We meet very frequently. We have discussions every day that are either informal or formal. Sometimes people have different goals, but if you listen to the leadership of Exploration Systems Mission Director in the United States, you will hear Jim Free, the new Associate Administrator, always talk about the importance of science to Artemis. And he's always asking us, probing us, what can they do? What can they do better, or what could they do more? So the integration is very, very close. That doesn't mean that we always can meet each other's goals. There's always a lot of negotiation. There can be constraints on things. As you can imagine, it's paramount for the human spaceflight missions to keep the crew safe. And so that doesn't mean that we can request things and they're automatically granted. But I always feel that that the other organizations are really trying their hardest to get the highest value they can out of Artemis for science and technology.
That's great. It certainly seems that way from my perspective as well. And we at Survey are honored to help with that. So that's fantastic. Let me turn it over to the floor and see if there are any other questions for Joel.
Greg, we were also hoping that the speakers would remain available for a panel discussion after the series of 4 presentations.
Yes. Okay, well, it doesn't appear that there's any brief questions right now. So Joel, we'll look forward to seeing you a little bit later. And thanks so much for your overview.
Thank you.
Great. Let's see. I will perhaps introduce the next speaker, and then maybe I can turn it over to my co-chairs for the last 2. And the next speaker is Dr. Tony Colaprete of NASA Ames, where I'm based. And Tony is the chief scientist, the mission scientist for the Viper mission, and he's going to be giving us an update on that. Lots happened in the last year. So, Tony, over to you.
Well, hello, everybody. Thank you for inviting me to give you an update, an overview, and a bit of an update on the Viper mission. I think most of us know about Viper, but I'll give a brief kind of outline of its mission goals and its objectives, and get into the science and the instruments, and then finally some traverse planning towards the end here. As we all have heard, I think the last decade and a half, our thinking about water on the moon and volatiles in general on the moon has dramatically changed. We've seen the moon going from what we thought was a relatively dry, airless body to perhaps hosting surface frosts, buried ice, bound water in the minerals, hydroxyl, etc. And this is all primarily from orbital observations, some impact observations, etc. So now it's time to get down to the surface of the moon and look at it at what I've always called the human scale. Really get down there, understand the phenomena in a way you can only understand it from really being on the surface like we were with Apollo. And so, as you heard from Joel, that's happening, not just with Viper, but with lots of other landed missions, which also include small rovers. So we are really going to be, I think, opening a floodgate of new information and excitement with these new observations, observations we just haven't had for the South Pole region ever. So Viper will conduct exploration science, which is a little bit different than our traditional planetary science. It originally had its origin in the Exploration Directorate at NASA, but now lives within the Planetary Science Directorate, which is fantastic because exploration is science and science is exploration, as Mike Boyle used to say, and Viper is the antithesis of that crossover between exploration and science. So this is a bit of a summary of where we're at right now. This is a bit dated. We passed our mission design review last October, and we're actually approaching, you'll see my final slide, a systems integration review this summer. Hardware is being built, flight hardware is being built. This is a dated slide 2. We did select 8 new science co-Is, and they've been integrated into the team fully and are at full speed ahead. So what is Viper? Viper is Volatile Exploration Investigating. The Volatiles Investigating Polar Exploration Rover is an exploration rover. It's looking at the distribution, the physical state, and the context and correlation of primarily water. It's really focused on water. However, it is capable of investigating all other sorts of volatiles, compositions, mineral compositions, geotechnical aspects. You heard from David King how important that was, et cetera. So we are trying to address what you see here on the figure on the right, the bounded area in the red, with the red dashed box. We are trying to understand get a better understanding of the potential of resources at the poles of the moon, in particular water as a resource. And so we are trying to actually build up enough of an understanding of the distribution, the physical state of the water, but very importantly, the context and the correlation of the distribution and physical state with the environment factors like sun, soil mechanics, temperatures, et cetera, so that we can actually start to build much better predictive maps, predictive capabilities as to where we might be able to identify and locate and assess the total potential resource anywhere at the poles of the moon. So that's what VIPER is really trying to get a start on. And the way we're doing it is by organizing where we explore into various into a series of thermal environments. And this was done to help us plan and organize our traverse planning. And it's really is situated around a designation of thermal environments that is a bit arbitrary. I show them here on the left here. We define surface environments where we think water ice could be stable on the surface, like a permanently shadowed crater. And then we say, well, where might we predict water to be stable over geologic times from the surface down to 50 centimeters? Because as we expect from thermal modeling, down at depth, even though the surface might be too warm, at depth there could be temperatures cold enough to stain water ice. So we've used thermal models to predict that, and that's what we call shallow, zero from the surface down to 50 centimeters. Then from 50 centimeters down to 100 centimeters, we call that deep. That's a deep thermal ice stability region, meaning ice could be stable at that depth. And then dry is in the top meter, we don't expect water to be, our temperatures at some point got hot enough that water would have sublimed and escaped. So the figure on the right shows the VIPER mission area and a number of craters, or the area organized into these four what we call ice stability regions. And you can see the red regions are permanently shadowed regions or surface stability regions. Green are shallow, yellow are deep, and gray is dry. So this is the VIPER surface segments. I won't go through all the call outs here, just the important ones like the mass cam. We use stereo vision for our navigation. It creates hazard maps in real time, stereo hazard maps. And we have, these cameras also act as science instruments. And we have a series of cameras up here on the mast and a series of hazard cameras at the wheels. And not shown here are a stereo pair of cameras looking out the back, the aft of the rover. So we have quite a few cameras that will be looking around all the time as we drive this thing in real time. We have down underneath you'll see in a minute, a mass spectrometer and a near-infrared spectrometer and thermal radiometer. And then out in front here, we have the Neutron Spectrometer system. That's the nose of our bloodhound, if you will, as we drive, always sensing for hydrogen. And then last, but definitely not least, this little feature in the back here is where the Trident drill, 1 meter drill, is located. As you heard from Joel, will be brought to the moon, delivered to the moon by the CLPS program on the Astrobiotic Griffin lander. This is an artist conception here, and my final slide, actually, I'll show you us driving an engineering unit of the rover off a structural mock-up of the lander provided by Astrobiology. Those tests are actually going on as we speak. Right now I'm at Glenn. I'll show you a photo of that later on in a bit. These are the four primary science VIPER instruments. I mentioned the cameras are being treated as science instruments as well, with all the accolades and responsibilities that each of the instruments get, including archiving data and everything else. But these are the four principal science instruments. We have the Neutron Spectrometer system, that's led by Rick Elphick, NASA Ames. It is, again, a two-channel epithermal thermal neutron counter. It is going to be able to tell us where the hydrogen is and how, and with the model, tell us the estimated quantity and depth at which it's buried while driving. We have the near-infrared spectrometer system, or NIRVIS, that's led by myself. It's a combination of imaging, multicolor imaging, thermal radiometry, and near-infrared spectroscopy. It's also on continuously while driving and drilling. We have the mass spec observing lunar operations, or MSOLO. This is led by Janine Captain out of Kennedy Space Center. And it will be able to measure gases coming up from the surface or while we're drilling between 1 and 100 AMU. It is also on continuously while driving and drilling. And I've said that now a couple times because that's a really neat feature of Viper is these three instruments are always on, always. And while we're driving in and out of science stations, while we're drilling, so we're having this continuous data set across the entire duration of the mission. And then finally, here's the regolith and ice drill for exploring new terrains, or Trident, led by Chris Zachney at Honeybee Robotics. It is a 1 meter percussive auger, and also has two temperature sensors, one at the very tip and one 20 centimeters up near a heater that allows us to measure subsurface temperatures. And also by using the two thermal sensors and heater, we can actually do a number of thermal conductivity and thermal properties experiments. So that's the payload that we're going to be using during the entire mission. So the payload, or the mission operations are primarily broken down into three types, or three modes. One is called rails driving. That's where we're driving between science station, and we're primarily focused on getting where we need to be on time and safely. Even in rails driving, though, we have all the instruments on. And then when we get to a science station, we turn into what we call prospecting mode. Now, prospecting is only different in that we actually take more color images with NIRVAS at waypoints, at driving waypoints. Otherwise, it's the same as rails with all instruments operating all the time. And this is just a little cartoon that shows some of the power of that. As we're driving along, we'll be sensing buried hydrogen, and if we come across a surface phosphat, NIRVAS will sense that, MSOLO will sense it if we're scuffing up volatiles. We're measuring surface temperature while we're driving continuously, so we get this continuous data set that we can combine into a much more powerful story of what we've seen in the places we've been. And then the last mode is drilling, or subsurface sampling. There we park and we prepare the drill for a 1 meter drill. We go down in 10 centimeter, what we call bites, 10 centimeter segments with depth. We bring up the drill, brush off the cuttings into a pile in the fields of view of NIRVAS and MSOLO. And we've demonstrated this many times in thermovac testing at Glenn Research Center. It's a fantastically simple yet powerful way to actually be able to profile and measure very quantitatively and repeatably water and other volatiles at depth. So the Viper mission area is this area over here, just to the northwest of the Nobile crater. This is the Nobile crater here. We're in this area. The yellow areas are areas of what we call safe havens. These are areas that have typically less than 70 hours of shadow over the summer season at the South Pole. And you can see they're scattered here and about. David was talking about this ridge down here near Shackleton. There's a number of these safe haven sites down there, makes it a very attractive place. Likewise, near Haworth, the Maston mission is landing over here, at one of the CLPS missions that Joel noted. So this area was selected because it had a variety of thermal environments. As I mentioned, we want to study each of these ISR environments. So we had to make sure we had it all four, and they were all equally accessible. The periods of shadow had to be short, and that's the yellow areas. And of course, we were a director communicating rover, so we needed to have direct line of sight at the same time as we had sun. The slopes and everything else had to be considered too. So it's a very constrained problem, and ultimately, after clearly a couple of years or more of site analysis, this was proposed to Thomas Spoken and agreed to as the mission area. Now, we haven't picked a exact landing site yet. That's in process, but this entire area is the mission area that we'll be working in. This shows a kind of a oblique view using a terrain model, shaded relief terrain model. This is a 1 meter DEM created from what we call shape from shading analysis. It uses NAC images to create a 1 meter posting DEM. And the colors here are the ISR types, again, red being PSR or surface stability regions. The yellow, bright yellow, are our safe havens, shown here. And we will be visiting all three of these major PSRs in this area, as well as some of the smaller ones. This just shows a really neat oblique view. This is our planning tool. So we do planning at 1 meter resolution or better. We actually, for synthetic modeling, go down to 4 centimeters for planning. And this just shows a really pretty view with our Viper rover down here for scale of the first large PSR we plan to go into. And so real quick, I'll wrap up with an example of the mission area, a mission area traverse. This is one that has been being studied using a tool called Sherpa that the teams developed, which looks at the average speed of the rover, slippage, slope, power, data, all the things that influence how quickly we can drive, activity durations, et cetera, and then adjusts it, puts variations about it, like good days and bad day variations on it, and can evaluate how robust a traverse is to success. I mean, this is a particular traverse that is very robust given our constraints. Well, you can hopefully see here, so here's the same PSRs that I just mentioned. This is that large PSR I showed in the previous slide. We land here and we drive towards the PSR, and this blue line is our traverse. And we, after visiting the PSR, each of these little squares might be hard for you to see, are science stations. We go into the PSR twice, actually, conduct mapping and then drilling activities. And then we drive, and you can see this long, continuous drive. That's us just getting back to a safe haven location. So as the Earth sets, we lose communication. We park ourselves in an area that has nominally almost continuous sunlight and wait out that loss of comm, which is typically about 14 to 18 days. Once the comm comes back up, we start driving again. And this particular traverse, we head over to this series of PSRs, visit these relatively smaller ones. I could say this is about 500 meters across here. And then we continue to this larger PSR and move over to a safe haven in this location. When the next lunar day, we come down into here, we visit this PSR, conduct all of our mapping activities, come back to the same area for hibernation, and then we do this long drive to this bonus PSR. This would be our fourth lunar day, and then come back to here. And we're actually looking for potential options for a 5th and even 6th lunar day. So given we have a much better understanding of the rover's capabilities now, the site analysis has really been completed, we're looking at really being able to extend our mission duration, we hope. This is a quick summary of this 4 lunar day mission. It's 111 days, Earth days total. We beat our full mission success in the first lunar day. It only takes us about a little under 10 Earth days to complete our full mission success. This odometry is just a total drive distance for the rover. This particular traverse through 4 lunar days, we did over 31 kilometers. And you can see the breakdown between the various ISR types, dry, deep, shallow, and PSRs. This is really exciting to me. We have nearly 2 kilometers of driving distance in PSR terrain type. That's really exciting. We have 32 science stations. And I didn't mention this, but in each science station, we do at least 3 1-meter drills. That's all accounted for in this traverse planning. So, we're looking at potentially 50 to 60 to 90 1-meter drilling activities over the course of the mission here. Right there, it says drill sites 78. So that's going to be a phenomenal data set. So just to wrap it up, where we are now, I already mentioned this up front, we are moving towards our systems integration readiness review, where we're basically saying, hey, we've got all of our pieces and our parts and our plans in hand, all the procedures and integration steps. We're ready to proceed to building the rover up and getting into environmental test. The instrument flight builds are nearing delivery. The NSS instrument had its pre-ship review already. It was phenomenal. It passed. It's getting ready to pack up and head down to Johnson for integration ultimately with the rover. Nervous and then MSolo come next, and then Trident. They'll all be done by the end of this summer and delivered. We've added 8 new science team members, boy, typos here, members. Last December, they're fully integrated and running. We had an awesome science sim just the last few days that they participated in, Operation Sim, and it went really, really well. Just some quick pictures here. Rover thermal, the Rover mock-up Rover engineering unit and thermal tests at Marshall Space Flight Center. This is a build Pathfinder at JSC. You can imagine putting together a rover like this is a crazy jigsaw puzzle, 3-dimensional jigsaw puzzle. So they've got basically a Pathfinder that helped them, figure out exactly how to put it together. And this is testing ongoing right now at Glenn, where you have a mock-up of the lander and ramps delivered by Astrobotic to Glenn Research Center. And this is what we call our McGrew. It's an engineering full-scale rover test unit. And they've been practicing separation from the lander and driving down the ramps in various situations, like one ramp higher, landed on a rock, and so on and so forth. So with that, I'll leave it, and thank you very much.
Excellent. Thank you so much, Tony. What an incredibly exciting mission, and it's so hard to believe that it's coming so close now. So I think that what we'll do is have discussion a little bit later, and I'm going to turn it over to Evelyn and Philip for the last couple of talks.
Thank you, Greg. Yes, it's my pleasure to introduce Sebastian Els, who is going to talk about MBRSC's Emirates lunar mission. And I think it's really great that we have the first MBRSC representative at the European Lunar Symposium. And I think with his last name, Sebastian was really destined to participate at some point. So if you can go ahead and share your screen, Sebastian.
All right, so I'm audible and the screen is visible.
Yes.
Yeah, hello, everyone. Thanks so much, Evelyn, for the invitation. Yeah, I'm going to give you a quick update where we stand with the ELM, the Emirates Lunar Mission, the Rashid rover, its science, the instrumentation, and the status. And of course, I'm giving this on behalf of the ELM development team here at MBRSC in Dubai. MBRSC is the Mohammed bin Rashid Space Center, and I'm going to say something about that in a moment. And of course, of all of our science collaborators worldwide, and a number of them are actually in the audience. So guys, if I say something stupid, please just step in and correct me. I see that somebody is trying to request control on my screen. I don't know if Akos is really want to do this. Otherwise, I say just deny. Okay. So the overview is just a brief overview of the mission goals and the brief of the mission. Then I give you a quick overview of the science and the instrumentation and the current status and the outlook. But just to put things into perspective, so the Mohammed bin Rashid Space Center is located in Dubai, and it is basically the main entity in the UAE, the United Arab Emirates, developing space hardware and satellites. So the UAE space program has been instantiated about 15 years ago, and it started with Earth observation satellites, which have been built quite successfully here in Dubai in the facilities. Built, then they have been launched and operated from the Mission Control Center here in Dubai as well. Then a couple of years ago, so about 5-6 years ago, you might have all be aware of the Emirates Mars mission. So there was then in 2017 the launch of this 100-year initiative, so that we have a human settlement on Mars in 100 years from 2017 onwards. This is, of course, needing the development of a number of technologies, facilities, and so on. And of course, robotic technology and technology demonstration, and to make the entire endeavor also cost effective. And in this context, of course, the moon is sort of a stepping stone. And henceforth, the idea was then pursued a couple of years ago to develop a small lunar rover as a starting point to get into this field of robotic exploration of planetary surfaces, because also the Emirates Mars mission is a orbiting mission, so it's not a surface mission. So ELM, or the Emirates Lunar Rover, ELR as well, but that's an obsolete one, I'm sorry, has four main objectives. So the main one is to prepare and demonstrate the national capabilities here to develop and operate a small mobile robot on another celestial body. Then the second objective is, of course, we want to do also science, which is relevant and useful for future lunar missions, as well as fundamental research. And we have also the goal to, or the objective to involve the public directly in the operations. I'm not going to talk about objective 3 and 4, but I just want to mention it for completeness here, that you understand what went into the requirements process for designing the rover. And we also want to attempt to survive the first lunar night by means of providing basic operations during the second lunar day. Now, the mission brief is, and I mentioned it already, it's a very small rover. It's a 10-kilogram class rover. We are not opting, so everything what you have heard by the previous speakers with all these gigantic and great missions, just change your mindset for the moment, because our entire rover has the mass of basically one of the instruments which have been shown today in the afternoon in the course of this conference. And we are aiming for an operational lifetime on the lunar surface for at least one lunar day. So the aim is 10 Earth days, but of course we're not going to be put on the ground just at sunrise. That's going to be probably a day or two later. And then hopefully we wake up also during the second lunar day. We will also make use of the now available commercial providers, which can give you a lift to the moon. The Japanese company iSpace has been chosen for that purpose. And this is also an artist's impression here, how such a rover would be placed on the surface. Now, the science objective of the Emirates Lunar mission is that we want to obtain data primarily with the goal to support future missions, but of course we also want to take fundamental science data. Something which is also important, the science package shall make use of the rover's mobility. That, if you think about when it comes to selecting the instrumentation, that has some impact of what to choose and what not to choose. And we are not targeting, our science package is not designed to target a singular location or area on the moon. So that is actually quite important to if you think about the requirements process for the instruments, if you say you want to be able, your instrument should function and deliver data in all locations on the moon, this excludes certain instruments immediately. And obviously, well, not obviously, but this is also quite a goal for us, is that we make the data available to the scientific community, meaning to all of you, so there will be an archive at the end of the mission. Landing zones, I call this landing zones because I'm not going to talk about the landing site itself. So targeted are 45 degrees northern latitude plus minus 7.5 degrees. We have 3 backup landing sites and we have 1 prime landing site. The prime landing site has been recently shuffled with the backup landing site, so there were some new requirements. That's also, if you think about it, when you take a mission with a commercial provider, you might not be the only payload on board. So if you design your science package, you have to think a little bit about, you know, do you really design an instrument to one particular location or that one scientific target or object, which you only can see at one location. So that was also the reason for us not to do so from the start. The new landing site will be announced in the very near future, but we think it's going to be a pretty exciting one. And the lander service here on the right is not provided by iFace. That is my colleague Salem just placing the engineering model during a recent desert test on the ground. So with this, I want to just dive quickly into the instrumentation and the science objectives or the science topics we want to address. Now, it's a 10-kilogram rover with all its subsystems. That means the science package is going to be also quite lightweight. And if you have a low mass rover, you cannot actually go much underneath the surface. So we are focusing on the surface properties at small scales, particularly the regolith particle properties, the lunar surface layer structure at sub-millimeter scale, thermal properties at the sub-meter scale, the lunar surface plasma sheath, so the photoelectron sheath. We also want to address dust transportation. And for the future mission technologies, we address trafficability, regolith mechanics, and we are testing some materials for lunar missions in the future, as well as rover controls, obviously. This is a picture which you might have seen already, but it shows in basically two images. One to the left image shows you the front view of the rover, and the right image is the rear view of the rover. Our main instruments, which we have on board. So camera 1 and camera 2 are wide field images. I'm going to talk about them in a moment. We have a microscope on board, long mirror probes, which measure the photoelectron sheath. And what you see on the wheel surfaces there, the colorful areas, are material samples. So because we are using very classical rigid wheels with a solid surface, but with grouses, so we have this what some people call otherwise unused real estate. So the idea is that we simply tap on some material samples and observe how they interact with the lunar surface regoliths. The cameras, so the two main cameras are wide field cameras. They have a field of view of 82 by 82 degrees. They're 4 megapixel CMOS color detectors, RGB. These cameras have been provided by our partners at CNES. The camera on top of the mast is gimbaled, so you have a full 360 view, up, down, left, right. And it's obviously the main navigation camera. The second camera is fixed at the rear of the rover, so it's constantly facing backwards. It's, of course, much closer to the ground and approximately 20 centimeters above the surface. And it also acts as a redundant camera for Cam 1 in case the worst thing would be that the mast does not deploy, so you have still a navigation camera which you can use. And I want to point you at the upcoming COSPA to the presentation and contribution by our partner, Zach Yarnum. If you're interested in the imaging system in more detail, please also join the COSPA conference. We have a small off-the-shelf thermal imager. These are the numbers which we have from the manufacturer, so about 3% to 3 Kelvin, and you get 39 by 30 degrees field of view. And it's fixed at the rear of the rover. The microscopic imager, we call it CAM-M, well, obvious reasons, is the same detector, the same CMOS detector as is used for the wide field images. The microscope is mounted at the front of the rover. It's pointing slightly forward, so the patch which you are imaging is about 20 centimeters ahead of the rover. And you get images with a spatial resolution between 20 and 30 microns per pixel. The goal, obviously, is to observe the undisturbed surface regolith layer. So this is something which I think we don't have at this scale. This has not been observed up to now. And we can also, of course, if you think about it, you drive, when the rover drives, there will be a trench. So if you just return to that trench you can actually take an image of the materials just underneath the surface. We also have a set of LEDs. The main goal here is just to provide some light if we want to take images in some shadowed areas, but also to reduce the contrast ratio at these scales. And if you think that you are at mid-latitude sites, you will have shadows. So in order to overcome potential contrast issues, we have a set of LEDs there. Here are some examples. So the one on the right, the top right picture is a view from the mast camera downwards. I hope you can see this somewhat. There is a pelican case, you know, these plastic boxes with a mix of sand and lunar simulant in it, and a couple of rocks. And what you see on the left, or the central image here, this is the view what ChemM actually sees. So here you have an example of a scenery, what you would see during operation. The slanted edges of the ChemM image, this is because the distortions have been taken out of it, and because of the angled view of the microscope of the surface, you have this these slanted edges, this perspective distortion. We have a set of Lunar probes on board. If you look at the vertical density distribution of the photoelectron sheath of the moon, there are not that many simulations around, and from the few which have been published, it is very interesting to see that right at the height of our rover body, there's the maximum density. So the solid line which you see here, these are the simulations by Horani from 2010, and you see the solid line shows you the photoelectron density with height, and well, basically the rover, the Rashid rover, is going to plow right through this densest part of the photoelectron sheath. Henceforth, it was kind of a straightforward choice to deploy a set of Lunar probes on the rover body, 3 of which are right in this maximum density range at altitudes where we expect the maximum density to occur, and the 4th probe is at the relatively close to the top of the mast. And then we have what we call MAD. This is the material adhesion and abrasion detection experiment. So we have, as I mentioned before, on the wheels between the grousers on these surfaces, we have different material samples and little experiments mounted. In total, we are at about 25. And these are provided by our external science partners. And the idea is that we monitor the behavior of how these samples, the regolith accumulation on these samples, the distortion of these, the abrasion of these materials with the main camera. So the right picture shows you an image taken from the mast camera of the wheels, and you can see with this wide field of view which we have, we can actually see 3 wheels in one shot, which is very handy. And we will be able to resolve dust grains in the order of about 0.5 millimeter on these samples on the different wheels. On the left, you can actually see the imprints. These samples are also leaving on the sand, on the regolith, so which will also give you quite a number of information about the surface. So what is the status? So if I take this image here on the left, you might think we are already there. No, we are of course not. So this is just an outreach picture during the field test, which was conducted earlier this year with the engineering model. But where do we stand? So the engineering model has been completed. already end of last year. We went through the TVAC testing campaign, the abrasion tests, and so on. There were a number of lessons learned which have been incorporated in an enhanced engineering model and in an updated flight model design. The flight model integration is going on right now. So I don't have any pictures, or well, I have pictures, but I'm not going to show them because they're showing you the status as it was a couple of hours ago, and that has changed already. So I don't see much point in showing this. We are doing then during the remainder of this year operations preparation and training, including our science team, obviously. And the launch is still in the previously announced launch window in Q4. So in this sense, everything is on track. And the lunar surface operation is foreseen to commence still in Q1 next year. These are our science partners, and there's still a few missing, but I didn't put the logos on because the paperwork is still in progress. But as you can see, it has grown quite a bit. We are about 30 scientists on this mission, and yeah, we here at MBRSC are very happy to involve all of them, and that this also then triggers a further grow of the community of planetary scientists here in the United Arab Emirates. So, and with this, that's the last picture, the last slide. I thank you very much for your attention, and I'm open for questions.
Thank you, Sebastian. So I suggest we ask you any questions there may be after the last talk. So with that, I'm going to hand over to my co-chair, Philipp Preis.
Yes, and we're now going to wrap up nicely the presentations of this session with another European perspective given by James Carpenter from the European Space Agency, and he will talk about the utilization of the moon for science and technology. James, we see you already?
Yes, excellent. So I just share my screen. Can you just confirm you can hear me okay?
Excellent, everything's fine.
Superb. Okay, so good afternoon, everybody. It's fantastic to be with you again. I'm very much looking forward to a European Lunar Symposium in person again next year. It's one of my favourite meetings. I've really missed it while it's been away. So, and it's also really a real privilege to be able to finish this off. And what I would like to try and do in this presentation is to revisit some of what my director, David Parker, told you in his opening talk, maybe to go into a little bit more detail on some of the topics that he raised. Also noting that many of the things I want to talk about have been talked about in depth by people during this meeting. So I've seen lots of presentations about the different lunar activities that we've been involved with. One thing that really occurs to me is that I'm struck by how things have changed over recent years. So I've been coming to these meetings for quite some time, and it's wonderful to see we've gone from here's my great idea to here's my flight hardware. And while we're not at the moon yet, we're getting really close now to getting some really fantastic activities on the surface of the moon, some great new science back. So it's, I think, an exciting time. And I hope that you can see that for us in Europe, it's also an exciting time with some real opportunities coming. So the first thing maybe just to revisit was something that I think Dave introduced to you in his opening talk, which was that our long-term vision, what we're aiming for in the longer term, is to have European astronauts, European science and European technology contributing to a future international station for research on the moon. Now, we don't know exactly when this is going to happen. We in Europe are probably not going to be the only people that do this. It's going to have to be an international effort to create something like this. But we're being tasked with preparing for this as a long-term eventuality, and that this should drive the things that we do now. We should be preparing ourselves to participate and to prepare this longer-term scenario. But we don't get there straight away. And so we have this intermediate scenario, what we're seeing in around the early 2030s kind of time frame. And in this, you see some of the different building blocks that Europe is building or preparing right now. So I've removed the banner from the top of this, so you can see in the top left there, we have the gateway in orbit around the moon, where in Europe now we are preparing our contributions to this, the habitation volume and the equipment that we're developing for the gateway. You can see, if you look really hard on the back left of that, you can see the Orion vehicle with the European service module on the back there, the first of which is getting ready to fly now on Artemis 1, with others having been delivered or in preparation now. And then as we go onto the surface of the moon, you see the European Large Logistics Lander. And so we have parallel industrial activities to prepare this. And following our next Ministerial Council meeting, which will be at the end of this year, we are hoping to get the mandate to go ahead and build this as a contribution to an international scenario on the moon. And what you see on top of this lander in this image are a couple of different kinds of things. So you'll see pressurized containers containing cargo to be delivered for crew to use at the lunar surface. You'll also see scientific equipment. You'll see a small rover there. You'll see on the surface a geophysical station. And so the idea is that this is a vehicle that can deliver scientific equipment, payloads, cargo to support an international scenario, both as standalone missions, but also as a contributor to Artemis. And so with this in mind, we're trying to work now on the infrastructure that we would want to have later on the surface, to the activities that need to prepare that infrastructure, and on the way we're going to utilize this surface infrastructure when it comes. And so broadly speaking, we break down the way we see utilization, so the use of this surface capabilities, into three domains, and just for the ease of the way we think about it. So in this early period of 2020 to 2025, we've been working on what we've called missions of opportunity. So this is really the first ESA science and technology on the moon, the first ESA payloads, the first ESA hardware to go to the surface to do science and technology preparation. And in this, we've been working with international partners, and I'll talk a bit more about that in a moment. But this has really been the first time we've been able to develop some of the expertise, develop some of the capabilities that will enable things that will come later. What we're planning to do from in our next programmatic period from that, which will start next year, is to start what we call early utilization. So this is really strategic research and technology preparation, things that are intended to prepare the use cases that will come later, as well as creating opportunities for nationally led science activities. And that would take us into this period of the 2030s, where we talk about sustained utilization. So this would be the continued utilization of infrastructure and capabilities on the moon for science, for technology, and for commercial applications. And so the things we do in this period that's coming should be the things that prepare that longer term use case later. So in this period of early utilization, or the first science and technology on the moon, we've had a number of activities. I know you've heard a lot about these during the week, so I won't go into detail on them all. But we've been looking at the first hardware to go to the lunar surface this year. We've been involved in the ANXA activity to access previously uninvestigated samples on the lunar surface that have been stored in a pristine state since Apollo 17, and we're developing other payloads for later on. One thing I'd really like to talk about, and I know that we have Joel here, and I want to take the opportunity just to talk about how important I think CLPS is. I think the Commercial Lunar Payload Services Program in NASA is, I think we'll look back and we'll really see that as being an extraordinarily important program for the world. I think it's opening up exploration and access to the moon in a way that is unprecedented. And certainly we in ESA are benefiting enormously from this partnership with NASA in CLPS, and is creating, I think, a new kind of capabilities and experience for us, but also I think around the world, a new mindset on the way that exploration can be done. And so I think it's just a really, really important program for everybody. We're also working with JAXA, potentially cooperation with CNSA on their Chang'e 6 mission, and developing some of these capabilities like Lunar Pathfinder for commercial communications and navigation, which you've heard about already. And also this LandCam X, which is a technology demonstration for precision landing technology, which we're planning to fly with a commercial lander and we're in negotiations about that at the moment. So at some point you should find out who that commercial supplier is. Something I think is interesting is for us in ESA, it's not simple to be able to procure services from companies that are not from Europe. And so there's the whole thing about commercial commercial procurement of services is something which is kind of new for us, and we're exploring how we can do that in an effective way. So I'm going to jump now to this end part, which was about the what happens in the longer term. And so we've been exploring and investigating some of these different options for what utilization of the moon, what we do on the moon might look like in the 2030 plus period. So some of you, many of you, I think, were involved in replying to a call for ideas that we had, I think even in 2020 now, where we were looking at ideas for things we could do with the European Large Logistics Lander. And from that, we produced a number of different use cases, some of which were linked to utilization and some of which were linked to infrastructure. Now, the things that we've studied are we've taken the European Large Logistics Lander EL3 as the technical boundary condition. So we've assumed delivery of hardware and operations at the surface using EL3. But these use cases, I think, give us a technical reference to understand technically, financially, programmatically, scientifically, what it would mean to do these different things. And that gives us a basis for how we would want to go forwards. So we've been looking at the exploration of polar resources using surface mobility to go from beyond what we've been looking at now. So perhaps I should have mentioned earlier, but when we think about things like Viper, for example, I think that is a really important mission. What we don't know today, we know there's water there, and you know, I remember that paper from 2010, those first results from LCROSS, where we knew then definitively there was water ice at the lunar poles. And this was a really important moment. And I think following that, Tony was absolutely right. We need to get to the surface and explore these resources. We need to understand their abundance, their distribution, and their utility. Okay? To what extent are these useful? How would we access them? How would we use them? And for that, we have Viper. We also have Prospect. We have our contributions to the LUPEX rover with Japan. We have other missions as well going to these lunar poles. And if you can pull these data sets together, if we can start to build real nice geological models of how these things are distributed around the surface, we can then go back and explore a deposit. So where we really think that there's a water ice resource. And that is something we've been looking at as a follow-on mission to these early missions to understand these lunar resources. We've looked at what it would mean to build a radio observatory on the lunar far side. We've been looking at geology and geophysics missions. I know many of you are involved in the preparations for a study we're planning to do into geology mission with robotics and mobility. We've been looking at geophysics packages that could be deployed around the moon. We've been looking at environment and space weather on the surface of the moon. We've been looking at what it would mean to have a biosciences laboratory on the surface, and also looking at in situ resource utilization, research and development, the things you might do there. And alongside that, we've been looking at different infrastructure studies, so things looking at power and an ISRU pilot plant, mobility, habitation and communications and navigation services. So it's a huge amount we've been looking at. It's an enormous amount of work done over the last couple of years to try and understand the technical basis for what's going to come. Now, I think what's important is it's clear that ESA is unlikely to do all of these things. This just financially, it's not likely that this is something that ESA is going to do everything here. But the vision would be that in this longer term scenario, all of these things will happen, or something like this will happen. And we would like to see European scientists and European community involved in all of these things as they happen, when they happen, but also to make sure that we've identified now where those areas are where Europe can really invest, where Europe can be a substantial player and leverage the skills and capabilities that we have in Europe. And so what we're working now on is working with our member states, with our science advisory structure, to work out which direction we should go, where those, what are those things that we should take forward in the next programmatic period, and how to do so. So with that in mind, we then think about this period of early utilization and what are we going to do on the moon in the latter part of this decade that helps us get to this endpoint. And so we'd be looking at activities in this period that really prepare this sustainable phase of exploration to follow. So we'd be looking here at technology demonstrations that prepare future ESA capabilities, and we'd be looking at science activities that also prepare these future use cases. And the things that we want to do within this decade, for most of those things, we're likely to have to start development during our next program period between 2023. I said 2023 to 2025, but between 2023 and 2025, we should be starting these developments. And something just for you to be aware of, in the fairly near future, so within the next week or two, we should be releasing an announcement of opportunity for a science reserve pool, which would be selected, then which would then sit in a pool which we can then draw on to deliver science on the moon during this period. So we'll be looking in that for science activities that could be brought to flight readiness within 3 years of selection for any given flight opportunity. And so in order to prepare this later period of exploration, or this early utilization period, we've had a number of activities ongoing to try and understand some different options here. So we've been looking at different technology demonstrations that we would be of interest to do. And we've been looking at science activities too that would be of interest to do within this decade potentially. Now, I won't go into the details of all these things, but we've had industrial activities and technology activities related to most of these things, and internal studies. And what we're doing now is, in the next months, is trying to work out what we would actually take forward. So these activities have been undertaken to support decisions that will be made in the next months on what to implement and how it should be done in the next program period. And the work we need to do now is to evaluate all of these and to prioritise them ready for what comes next. And so with that in mind, I guess just to bring this to a close, I think the key message would be, I think that we have a very exciting future ahead. I think that we are at the beginning. I think somebody said earlier, the lunar renaissance is starting, and it really is. And I think over the next couple of years, we'll really start to see this happen. I think this decade is going to be a really exciting one of transition, and I think that there's a very, very exciting future coming in the 2030s. And we appreciate very much your support and your engagement as we prepare the future. And yeah, thank you for this conference. Thank you for the European Lunar Symposium. I think it's a fantastic meeting. Thank you to all the organisers and everyone for participating. And I'm very much looking forward to seeing you all in person next year, I hope. Thanks very much.
Thank you very much, Jane. Talk. I think we now have 12 minutes left for questions for all of the speakers of this session. There's already 1 or 2 questions in the chat. I have one immediate question, if I may, to James, regarding the 2030 plus missions that you mentioned that do rely on the EL3 capability. So to what extent are they also being developed agnostic of this EL3 platform? So could they also be placed on another service?
In principle, yes. So we've taken EL3 as the, if you like, the reference case, the reference boundary condition. But if we think about longer term utilization, there is no reason why that utilization needs to be one-to-one with the EL3 lander. So I think what we're looking forward to is really an international scenario for exploration of the moon, and it's this scenario in a broader sense that we'll be looking at.
Right, that makes sense. There's one question in the chat. What is the status of the lunar Eurohab habitat? Asked by Serge Chevrel. To you, Jane.
Sorry, what was the question?
What's the status of the lunar Eurohab habitat?
I'm not entirely certain what that is. I mean, we've had studies ongoing to understand what it would mean to develop a habitation capability on the moon. So those are ongoing internal studies at the moment, and there may be some industrial studies to follow. But that specific example, I don't remember it, but that may just be me.
Right. I have another question if there's no one else. To Joel, actually, on the CLPS missions. You mentioned briefly that some European payloads are already pre-manifested on one of the or some of the opportunities. So to what extent are the scientific requirements of those payloads dictating the requirements of the mission, or are they prioritized in any way for other payloads or for the lander itself?
Well, I would say first, in order to reach agreement between the United States and another organization, we try to make sure there's an alignment of scientific objectives so that we can both satisfy our individual scientific objectives when international contributions are included on CLPS delivery. Then once NASA's agreed to have another organization participate in CLPS delivery, we seek to find a compatible delivery. When NASA pre-selects, today, we pre-select the landing locations to satisfy certain U.S. advisory scientific objectives. So we can project ahead of time what locations we believe we will do the landing in. But of course, we only confirm that once we have the entire instrument complement defined. So NASA will then look at a complementary supportive grouping of instruments and investigations to go to a particular location. Once that's confirmed, we actually manifest the particular instrument on a particular landing opportunity. And then that instrument science team becomes part of the team working with the commercial provider to define many of the details of that delivery, the very specific landing location. It could be the orientation of the orbiter of the lander after it's landed, the duration of the operations, in addition to all the standard things that would be related to the instrument, such as the data and the power requirements and things like that. So it goes in several different stages. It starts with the general agreement of the objectives. Are they do they meet goals for both the U.S. and the potential partner? And then it goes to, so what specific CLPS landing opportunity really makes sense for this joint activity? And then finally, it goes to the very details being planned by the group of payloads with the CLPS industrial provider.
Philip, I have a question. Yeah, so and this will be for both James and Joel, and so James, when you use the words lunar renaissance, that just captures it so perfectly, and I love it. And I was thinking back to the original European Lunar Symposium in Berlin, and seeing you there, and you had talked about a mission that was since canceled, I remember, and you're not alone in that fate. We had Lunar Prospector, which was canceled, but Viper arose from the ashes of that, and I think that we're here to stay. But what I'd like to do is ask both you and Joel about both the opportunities and challenges of working across the pond, you know, creating these opportunities together. So James, maybe start with you.
Sure. A time difference. Somebody's always doing it at a very unsociable hour of the day. So somebody loses in every meeting, right? The other thing, I think that we have our own process and our own programmatic cycle. So decisions get made at a certain time. There are certain hoops we have to jump through, certain consultations we have to make. There are certain times when money comes and times when it's gone. And so I think getting things synced up that way can be a little tricky sometimes because we're not always naturally in sync. I think we have our own strategies and objectives that we've been given, and so trying to get these things matched up. And so I think that we have different systems, and so getting those things in sync can be a bit of work. But especially when it comes to the science, for example, like the science is the science. I think everybody knows what they want to do. I don't think that I've never come across something that the European scientists were saying, this is really important, and the US people say no. So I don't think that we have a disagreement. I think that we are very, very much aligned in terms of what we want to achieve. Also in terms of the general philosophies, like the way that data should be available, the way that that science should be for the benefit of everybody. I think a lot of these principles are aligned. So my personal experience of working together in the last years has been extremely positive, and so we're very grateful for the support that we've had from NASA over the last years.
Wonderful. Joel, I wonder if you have a perspective on that. Thanks, James.
Well, I would agree with what James said. He talked about time zones. He talked about where you can spend money, and the fact we both the U.S. and its partners have different historically developed cultural processes that we use. There's one point I would add is that it's important for us to recognize that the way we're doing this today is different than it was planned even 10 or 15 years ago under prior efforts. We really, in the US, and I don't think we have a disagreement with ESA or any other partner on this, we really are looking at how do we maximize the benefit for science of this hybrid approach between humans being available on the lunar surface and also robotic and automated systems. It's not one or the other. We should get great scientific value of exploiting how both of them operate. But also in the near term, that in the US, we're trying wherever we can to use this commercial service approach. Again, ESA is also exploring this. But that's a very different way of doing business for us, whether it's shipping equipment to the International Space Station or having partners to develop human space vehicles like Commercial Crew or the Human Landing System, but also the service delivery approach we have selected for CLPS. We've done this to test a new paradigm. We believe it's going to be successful, and if it is, it's going to mean a much greater frequency at a much lower cost of opportunities to do science on the moon and eventually other places. And at the same time, it means we step out of our comfort zone and in the US and we surrender the details of the design and the operations to industrial firms. Thomas Zurbuchen has talked about the risk of this when you do something new. And he has pointed out that we don't have the same level of insight, for example, as we do in a traditional NASA science mission. For example, when we land the Perseverance rover on Mars at NASA, we can look at each other and say, we have done, or deploy the James Webb Space Telescope with our partners. We could say, we have done everything we could think of to make sure this is successful. That's not the approach we're using with commercial lunar payload services. We have these very, very skilled, very enthusiastic and entrepreneurial companies, and they've gone off and found similar launch vehicle providers. But we are buying a service. We are not doing it ourselves, and it is a very different way to operate.
Thanks so much to both of you. Appreciate those responses.
There's one hand up. Dr. Prasad. Please go ahead.
Hello, am I audible?
Hello, yeah, we can hear you.
Yeah, so in one of your slides, you have mentioned about International Lunar Geophysical Network. So what exactly the configuration would like to be? And then it would be a single mission or a multiple cooperative missions?
This is Joel Kearns. I'll mention that the Lunar Geophysical Network, the LGN, that was recommended by the U.S. Decadal Survey for Planetary Science and Astrobiology, is a mission that requires multiple sites for measurements to be made at the same time over long periods of time using specific instruments. And it's a very ambitious mission. It's one that's been talked about for many years. It's probably one that could be augmented or enhanced perhaps with a human component, although we'll have to look at that. And I think there are many opportunities for international cooperation on such a system. It's a system that would have to have very long life and operate at many different locations on the lunar surface in order to generate the data that's needed.
So maybe worth mentioning that in ETA we've been running studies into geophysical stations, So long-lived geophysical stations that could be deployed on multiple missions on the moon. And we're looking at that both in the context of robotic missions and also potentially something that could be done in human missions too. So in Europe, there's a very strong heritage in geophysical instrumentation. And so I think that's an area where there's certainly room for cooperation between Europe and the US.
Yeah, that's a good news. But at the same time, what I understand is like it would be a multiple missions spanning around a decade, and there would be a large set of international cooperation. Is that right? It's not a single mission; it's a multiple missions.
I guess my comment would be it depends on how you define mission. I think you need all the different measurements at different locations taking place over a very long period of time to actually meet its objectives. So when I think of that, I think of it as one mission, but it needs many flights over a long period of time to accomplish its objectives.
Yeah, that's interesting. Let's look forward for that. Thank you.
Okay, I think we can accept one last question of Simone Pirota, right? You raised your hand twice even.
Yes, thank you. Hello, everyone. Thank you for the interesting presentation. My question is related to enabling resources. I was just thinking that this community is very close to the final application, to the science and the final application, but of course there are enabling aspects like the transport and also the communication that can become quite critical in view of a very intense season of presence on the moon. So my question is, especially to Dr. Kearns, if you have the sensation that there is a need of an upgrade and a further development of the ground part, the ground segment, because we saw several projects related to constellation and flight segment for a very effective communication system to the moon for this coming decade and this coming season. But is there the sensation that the ground segment it's quite close to the limit, or there is a need of upgrade of the DSN, for example, network or STRAC?
I guess I would comment that NASA in its Space Communications and Navigations group is always looking at what communications and position and navigation and timing needs will be required in the future for both traditional robotic science missions and the Artemis and the Moon to Mars efforts to go out to Mars. And that, and I must tell you, I'm really not qualified to speak about the details of that, but I know that the ground segment, such as for communication, but also other aspects, is being looked to determine what needs to be put in place so that the space operations can be successfully accomplished.
Right, thank you.
Maybe I just say something. So we closed. Joel mentioned earlier the importance and the challenge of humans and robots working together. This is a point like my backdrop is all about that. You can see that, right? It's about humans and robots working together, and that's because we are in our director in ESA. We're the director of human and robotic exploration, and our director is always talking to us and saying to us, "But how do the humans and the robots work together? What does that partnership look like?" And I think that's what the future is going to look like. That's the future we've been asked to try and build, is one where humans and robots are working on the moon together, doing the things that they're best at and providing value together. And I think that's something that we're interested in exploring. It is a challenge for us.
Thank you, James. Sorry, just to mention that I had in mind also this topic because we are experiencing with the scheduling of, for example, for Argo Moon mission, which is going to depart with Artemis 1, we have to compete with other 13 CubeSat, and it's already very hard to find, the time for the station. So when the traffic is going to become very high, I think that for sure your colleague of the communication departments are thinking for a future season when there is much more capabilities in terms of traffic. Anyway, thank you for your answer.
Maybe just worth mentioning on the communication side. So something you heard about in one of the previous talks was about Moonlight and Lunar Pathfinder. And this is, on the east side, trying to create a partnership where we can create the commercialization of communication services and navigation services around the moon. And already now we have, through Goonhilly Earth Station in the UK, commercial lunar deep space ground station that is available for commercial access now. So I think that there's an opportunity there as this need for data back from the moon increases, and you've just demonstrated that happening. So I think that there are opportunities there for commercial access for data services too.
Clear, thank you.
Okay. So I think that's the end of the questions. I'd like to thank all of the speakers in our session today. Thank you so much for sharing your perspectives. The future of lunar exploration is truly international in nature. And I'd also like to thank my co-chairs, Evelyn and Philip. Thanks, everyone.